Okay, so welcome everyone. Good afternoon today. I'm going to be talking about planning for exploration. It's going to be a bit of mapping and planning. I'm going to be talking a little about this mapping pipeline that I developed using a custom written data structure that I didn't write, that was written at DreamWorks actually. So we're going to talk about that, and then from there on, we'll also talk about frontier-based exploration using that mapping pipeline. So, wait, what's going on? Okay, so to start off, this is going to be split into two parts. So the first part is going to be mapping, and the way I thought we'd do this is that I'll sort of walk you through the slides for the first part, and then we'll have a quick hands-on session. That way it doesn't, the theoretical part doesn't get too long and boring, and we can sort of keep working through things as we go through the slides. So the first part talks about mapping, and I'll start with occupancy grid maps. So what are really occupancy grid maps? So it's some representation of space, right, that is used by a robot to reason about its surroundings. And typically what we do is we have, like, say, incoming LiDAR point cloud data. And in order to build these grid maps, we discretize them into either pixels or voxels, depending on whether it's 3D, 2D, or 2.5D. So those are the different kinds of variations that you can have for these grid maps. Sorry? Okay. The pipeline that I'm going to be talking about is a 3D mapping pipeline, but you can obviously take 2D slices out of it and use those maps as well. We use probability to model occupancy, and how we do that is we start with a prior probability of 0.5, right? And then as we update the map and we update each voxel, if you're marking the voxel as being free, then its occupancy probability falls below 0.5. So any cell that's free will typically have a probability which ranges between 0 and 0.5. Similarly, when we mark a cell as being occupied, we add something to the prior probability. So the probability typically ranges between 0.5 to 0.1. Cells that are not updated, which are completely unknown, stay the same. So their probability remains 0.5. This is like a figure that, sort of shows the discretization at different resolutions. And this is from Cyril Stackness's paper on Octomap. And you can sort of make out the different voxel resolutions for this tree. Next, I'm going to talk about raycasting. So this is kind of like the most critical step when you want to build grid maps, because this is kind of what we use for updating the entire map and for updating each cell. And typically what we do is we draw a ray from the sensor origin to each point within a point cloud. So you have a LiDAR point cloud that you get from a sensor, and you have an origin for that point cloud, and you start with drawing a ray from that origin to each point as you iterate through all the points in the point cloud. And then we basically try to figure out all the voxels that particular ray intersects until it reaches the final point in the point cloud. So all the voxels on the way to the final point are marked as free, right? And the last point in the point cloud, the voxel that it intersects, that's assigned a hit, right? And it's marked as occupied. And one important thing to note here is that we actually use log odds to indicate the probability of occupancy. So we don't actually use pure probabilities here. And the reason for doing that is because when we do these updates, if we use log odds representation, the updates actually become additions and subtractions. So it's additive in nature. as opposed to working with pure probabilities, in which case we'd have to multiply them as we update each voxel. So that's like an important distinction to note. Yeah, so just giving you a quick overview of like the data structure. It's this data structure that's called OpenVDB. And some of the key characteristics of this data structure is that it's unbounded. So it, it doesn't have any size restrictions. You can build very, very large scale maps using this data structure. And it's optimized for sparse volumetric data. So this library was actually written at DreamWorks, and they use it for rendering some of their movies. So it's so in movies that have these sorts of synthetic graphics, they tend to use these things called level sets, which are actually hollow solid structures. And because of them being hollow, they're actually sparse, right? The data that they have is actually sparse. So this library was sort of written to be able to, it was optimized for those kinds of structures. And it sort of works well for us as well, because like you can have sparsity in like large scale maps, right? So so for the same reason, it allows for very fast access. I can share the exact paper, which sort of dwells more into the details into how this data structure works. But typically, like when you start accessing the map, you use this object called an accessor, and the accessor actually gets cached in memory, in CPU memory. So the accesses that you make with time sort of speed up because they get cached. So that's something cool about it. And it's also very general, right? So you can have different kinds of grids. You can have a Boolean grid. You can have a grid that stores floating point values. You can have a grid in which each voxel is actually a vector of values. So it's pretty versatile that way, and you can use it to store any sort of data that you want, essentially. In my case, I'm essentially using this to store log odd probability values for each cell in the grid, right? This is kind of what the hierarchy of the data structure. It's basically like a tree, and it has a single root node, and then typically it has two sets of internal nodes and a leaf node. And this particular topology is predefined, but as the map grows larger in size, this tree actually grows along the breadth, right? So the internal nodes essentially, they expand as the map grows, but the depth of the tree remains constant. So I think for that reason, the search times through the grid are sort of like fast as compared to something like Octomap, because Octomap sort of grows in depth as the map increases in size. So that's like, I think, one key difference between this particular pipeline and something like Octomap. The leaf nodes are essentially the nodes that actually encode the voxels. So each leaf node is typically 8 cross 8 cross 8 voxels in size. I've also mentioned like the like a relevant publication below that you could potentially refer to in case you're interested to read more about this. Next, I'll just show you a couple of videos to show you how this looks. We'll be doing something similar in the hands-on session as well. It's actually going to be the same bag file. Yeah, there's nothing special here except maybe I should have added some memory and time benchmarks. But yeah, this is a map of NSH, and we basically have raw LiDAR data that's being fed into Loam, and then Loam post-processes that and gives us these accumulated point clouds. And we essentially take those accumulated point clouds and then do raycasting on them to build this grid in 3D. yeah, the nice thing about this particular pipeline is, when we use this for the DARPA Sub-T challenge for the aerial platforms. And in large scale environments like tunnels or caves, this actually scales really well compared to Octomap, which sort of tends to get progressively slower. So that's like one major advantage that I think it has. I don't have very hard numbers on that because I haven't really done proper benchmarking. But that's something that you can do in case you're interested with the example that we have later on. Yeah. So yeah, the figure on the right is like a 2D slice that you take from the 3D grid, and it's split into two parts. So the left part is actually the occupancy, the 2D occupancy grid. The figure on the right is actually showing you frontiers, which are basically marking the boundary between known space and unknown space. So the frontier pixels that you see are the ones in white. The pixels that you see in gray are actually free, and the pixels that are black are unknown. In the figure on the left, actually, it's the opposite. The free pixels are the ones in white, the occupied pixels are the ones in black, and the unknown pixels are the ones in gray. So just be mindful of that difference. But yeah, this is actually, as we get to the end, we can sort of see that the circular portion is actually the water tank that you can sort of make out a little bit. But yeah, we'll be doing this on our own later on, so we can take a better look at that later. Next, I'll sort of walk you through the code just to, give you a sense of what is really happening in there. So if you want to maybe open this on your own computer, I will pull this up here as well. But yeah, let's see. Let me try to get this here. Okay. Okay, so we're gonna look at the exploration node, and let's start at line 14, which is actually it's a callback, but essentially and this is kind of like the main map building part. So what it does is it takes in a point cloud message and a corresponding odometry. So this is actually assuming that you have Loam running on your system. This uses Loam's outputs. So Loam actually outputs this accumulated point cloud, which is called a Velodyne Cloud Key Pose. And it also gives you a time synced odometry message with that. But in case you want to use it with something else, you can just sort of change this around. And you might want to use some sort of like a message filter to do some form of a sync between the odometry and the point cloud, so that we don't have big errors while we're doing raycasting. So we need the odometry that corresponds to that particular map. But yeah, I mean, that depends. Like if you have a map that's already in the global frame, then you don't really need odometry. You can just use the origin information of that particular point cloud to be able to do raycasting. Yeah, so what I do here is I basically sort of crop the incoming cloud. I just sort of reduce the size because I want the horizon for planning to be slightly smaller. So typically the Velodyne 16 that's been used to generate this data, the range is between 90 to 100 meters. but we sort of don't want to plan for that longer horizon. So we sort of box crop it. So you can change the size if you want to. I think right now it's set at, let's see, box, yeah. So right now it's set at 25 cross 25 cross 25 meters. But that can be changed. You can make it anything you want. And then this method, essentially what it does is that it basically does a transform, because this particular message is published in a camera frame convention in which Z is forward instead of being up. So we sort of flip that around to make it Z up. And then this is the main raycasting method that I will talk about next, that essentially builds the grid based on this information that we give it. So let's go do that. Right, so this is that method. It's kind of long, but yeah, I mean, essentially we have these things called grid accessors. So this global map that we're trying to build is actually a float grid. So each voxel can accept a float value, which is the log occupancy probability, right? And we have these accessors which essentially allow you to access each voxel in the grid. And that's kind of how you get access to, that's how you define an accessor for the grid. And then you basically define the origin from where you want to start raycasting. And we start by iterating through the cloud, through the incoming point cloud. And we do this thing. So the grid basically has two spaces that you can work with, right? One is an index space, which is basically IJK, right? Because it's a grid, so it's like a uniform IJK index space that it has. And then there's a world space, which actually corresponds to continuous coordinates in the world frame, right? And we can actually keep transforming between the two. So we have the ability to get a corresponding voxel index for a particular world coordinate, right? So that's kind of what we're doing here. And then we define something called a direction vector. And we sort of normalize that, so we get like a direction unit vector. And then the grid allows us to define an array based on a unit direction vector and a start point, right? And then we basically start stepping, from the origin to the point in the point cloud, and that's what we do here. Wherein what we're doing is we define this, I'm forgetting what the full form for this is, but let's just call it DDA for now. And this basically allows us to step through each voxel along the ray. And this particular method allows us to get the coordinate for the voxel. And then we get, this particular method allows you to get the value that's actually stored inside the voxel, which is the log occupancy value, right? And if it's less than a certain threshold, so this is actually the threshold defined for a voxel that may have been visited. So the reason I've put this condition here is to basically prevent voxels that are sort of already cleared out around the robot. So what I try to do is, as the robot moves through the environment, I clear out voxels around it in a particular bounding box to say that, okay, all of these voxels are seen, so I don't want to update them anymore. And this is basically done to prevent the generation of frontiers repeatedly in areas that the robot has already visited. And the reason why that happens is because a lot of times the robot is flying through these environments in which, you know, you have these small holes wherein the laser will find these points, you know, randomly that are sort of going through walls. And that causes a lot of noisy voxels to form. And this is sort of a way to deal with those noisy voxels, because the drone can never actually reach those really narrow confined spaces. And because it cannot reach them, it can never really clear out the frontiers there. So we sort of use this as a way to like manually clear out those frontiers. So we don't update those voxels. We just say, you know, the drone's been to this area, and we don't sort of want to update this anymore. So we just do that. But yeah, essentially, if it's below the threshold, which means that it's not been visited, it's not been cleared, we set the value, and we basically sort of, it's thresholded. The thresholding is basically defined here. If you look in the config file inside the package, these are sort of like these parameters that we define. And these log occupancy values are actually kind of standard in the sense that I have actually taken them from the Octomap paper. And based on whatever testing I've done so far, they seem to work fine. So essentially what these values mean is that, you know, the log occupancy value that you would assign to the first time you update a cell as being free would be minus 0.1. So it's on the other side of 0, it's negative. And we're assigning a slightly higher weight to the positive side, to the side wherein we are marking a voxel as being occupied. So we assign that a value of 1. And how the updates work is that if we update that voxel again, so say if it was free, and then we again update it as being free, then the voxel's value will become minus 0.2. So they add up, right? They don't get multiplied, they get added up. Similarly, for an occupied voxel, if its value was already 1, and if it is again found out to be occupied, then it becomes 2. And then we do some sort of a thresholding in which we define these max-min thresholds. So the maximum log occupancy value that a voxel can have, an occupied voxel can have, is 3.5. Similarly, the minimum value that a free voxel can have is minus 2. And these values actually, when you convert them into probabilities, actually reflect the extremities of the occupancy probability. So minus 2 corresponds to like a really small value that's close to 0. And 3.5 corresponds to a really, a value that's extremely close to 1, essentially. And then we have something called hit thickness, which is, this is sort of like a tweak in which if you want to have like thicker walls, you can actually increase the thickness. So right now the hit thickness is 1, which means that every time you raycast to a particular point in the point cloud, you get 1 voxel that's occupied. So we can increase that to 2 or more. So if you want thicker walls in your environment, for instance, then you can actually increase this. And then vox size is essentially the resolution of the grid. So that's in meters. So each voxel currently corresponds to 0.2 meters in real world space. Okay. So that's kind of what we're doing here. We're checking whether we're basically checking for thresholds for log occupancy values, and depending on whether we have reached the point in the point cloud or not, we assign a voxel as being free or occupied. And that's kind of what happens here. And this step basically allows you to step as you move along the ray. So that's kind of what ray casting really is, and that's how it's done in this grid structure. So so now we'll move on to the hands-on session, and I'd like you guys to maybe look at the first part of the README, and let me know if you already have this set up. But yeah, this is the part that I'm referring to. There's a back file that we need to play, and the links for that I have attached in the in that document. But I think I also sent it out on Slack. Let me get that out. So yeah, so let me know. Maybe we can do we can have hands to show how many of you have sort of set up or need help or anything like that, and I'll sort of wait, and then I can start running this on my system and show you what the outputs look like.
We have one hand. Do we have more?
Sorry?
I see one hand from Yoyu. Do we have more hands? Or yeses, I guess. We have two.
Hi, Rohit.
Hey.
In the meanwhile, can I ask a simple question?
Mm-hmm.
I didn't test the OpenVDB thing very in detail.
Mm-hmm.
And I'd like to know if we can use it in a multi-threading manner, by which I mean, can I have multiple reference to a occupancy grid and query the grid at the same time?
Right. So actually, there was a paper that came out from NVIDIA about this, in which they were actually trying to, I think they had a CUDA implementation of this library. But I haven't read that paper in detail. I can forward you the link to that paper, and you could potentially look at that. But in terms of parallel access right now, it's not, I don't think this grid is sort of, you can do that, at least accessing.
So as long as you don't modify it, I mean, you can access it as much as you want, I think. But as soon as you start modifying things, then it becomes complicated.
Mm-hmm.
So it's assumed that it's thread safe. That
yes, I think yeah, the access is thread safe, but yeah, writing isn't.
Right. Okay. So it's like single writer, multiple reader kind of situation. And I think the way, Rohit, correct me if I'm wrong, but I think the way this is used right now on these render farms is essentially everybody gets a copy of their grid.
Mm-hmm.
The computer, they run on the computer with each grid, and then then you merge these grids together.
Right. So so what Basti is referring to are Basti, are you talking about submaps, or are you talking?
No, I'm talking about how OpenVDB is used for, let's say, making Toy Story or something like this.
Right. Yeah. I think the merge operations are pretty fast. So so I think they sort of, I'm not really sure how they do it, but yeah, they probably split it up and then sort of merge it together later on.
Right. I think if I understood it correctly, the merging is fast because you basically have these two trees.
Yeah.
And you essentially can traverse that tree kind of in order at the same time, so you don't have to essentially match
Mm-hmm.
one leaf against the whole of the tree, you can just match basically the two trees to each other.
Mm-hmm. Mm-hmm. Um, So yeah, just to sort of give you a broad overview of like how the package is structured. So while the stuff is building, um, so we have the tutorial here. The exploration node is like sort of the main node that builds the map and computes frontiers and also plans paths to them. There's a separate sort of a support library of support functions that I wrote, and this is like this is not the full-blown version because that version is like over 3,000 lines, and it's kind of overwhelming to deal with. So I sort of wrote a shortened version, which basically has all the utility methods one needs to work with the grids. So so anybody who sort of wants to get a sense of what are the different ways in which you can work with the grids, you can sort of go through these methods and look at them and see what they're doing. But essentially, the key idea is that you have these grid iterators, and these grid iterators can allow you to access cells that are either, so the cells in themselves, they can have multiple states. So a cell can be inactive in the sense that it's never been touched, it's never been updated, and it can be active, but it can be active and then still have some sort of a background value. Just a second, I'll just close my window. So cells can be inactive, they can be active, they can hold values in either of the states, and you have iterators that allow you to loop through cells in different states. So you can loop through all cells in the grid, or you can loop through cells that are only active, or you can loop through cells that are inactive. So you have different ways of like iterating through the grid. And then the grid iterator essentially allows you to access the voxel and get the value that's stored inside. So that's kind of like the basis for working with the grid. And then, you can build your own things on top of that, in the sense that you can have, so they also have bounding box iterators, which are basically, you define a bounding box based on a max and a min coordinate. And then you can define an iterator that specifically loops through only that bounding box, right? And even within that bounding box, you can specify whether you want to loop through all the cells, or you only want to loop through active cells, and so on. So there's a lot of flexibility there. So, based on that, you can sort of build your own custom iterators as well. Like if you're comfortable with actually traversing the tree and, accessing all the nodes, then you can like write your own custom iterator. Or in some cases, like you know, if you want to build an iterator that sort of you know, samples a sphere, a spherical shape, for instance, then you can also define a point cloud of any shape. It doesn't have to be a sphere. It can be any shape that you want. And then what you can do is you can essentially get the closest voxel to each point in the point cloud and iterate through that, right? So there are methods that enable you to get that transform instantly and quickly, and that gives you a lot of flexibility in being able to sort of, you know, iterate through any sort of shape that you want. Let's see. So yeah, so you know, these methods, for instance, they're basically, you create bounding boxes that are in index space, right? And then you can set different voxel values inside a predefined bounding box. These are similar methods that way. You know, you can, then I have methods to do clustering. They're not really nearest neighbors, they're actually I mean, these are nearest neighbors. Yeah, so, you know, there's different methods. I can sort of like, this is actually a really simple and easy example that, you know, one can look at, is to sort of, you know, this is kind of how you define the loop in which you get an iterator. And in this case, it's going to iterate through all the values that are on, so all the cells that are active. And then, you know, it's just a regular for loop. And using the iterator, you can essentially set a particular value for that voxel. So in this case, it's looping through all the voxels that are active in the grid, and it's just setting their value to whatever value that you want to set it to. I'm not seeing a lot of text. Could people update the chat with letting me know if they've been able to set up the workspace, or are they still waiting? I guess I'll start once like more than half the number of people have sort of managed to set it up. Yeah, I think we can start. I think there's, yeah. So I'll start with running things. If you want to follow along, just look at part 1. Right. So you just need to open 3 terminal windows. First, run a raw score, and then in the second window, source your workspace. Make sure you set use sim time to true, and then you can basically launch this particular launch file. Once you're done doing that, you can open another terminal window and you can play back the bag file that I had uploaded earlier. I'll just do that here now. Let's see. Launch. this should open up RViz. I'll just move this out of the way. Okay, and then we can start running the back file. Make sure you run the back file the way it's written in the README because that helps you skip like the initial 15 seconds, and you also need to use the clock flag to ensure that sim time is run using the back file. Okay, so started running the sim file. So yeah, so this is kind of this is NSH level 2. And it's actually, I think this is just probably G walking around with a sensor and gathering data. And if you want to play with stuff, you can look at the YAML and you know, look at the part that says hands-on session 1, and sort of feel free to sort of change the values. I have another config added here which reduces the voxel size, so it's actually increasing the resolution, and you can try that out, see how that looks. You can also sort of tinker with the log occupancy values for freeing up cells and for marking them as occupied. So one good thing about using this particular way of updating the voxels is that it actually inherently removes noise. So for instance, one particular problem that we had when we would always fly the drone was that, you know, in dusty environments, it throws up a lot of dust. And the dust particles actually show up as very tiny, tiny points, right, in the point cloud. But because they're moving, they might appear in one particular message, but not in the other. And the cool thing about that is that, you know, you might mark that dust point as being occupied in one update, but then in the subsequent update, if you have enough rays that are actually passing through that occupied voxel and you know, marking it as free, you actually change the state from being occupied to being free. So it inherently removes noisy occupied voxels that way. So that's kind of a good thing with using like this sort of a grid mapping update rule. You don't have to worry about dust. But having said that, you can still, you know, you can see that there's still some noise. Like here, you get these hits from the LiDAR. Some of them are actually kind of reflections that you get off of these light assemblies and things like that. Yeah. One thing to note here is that this particular way of building the grid doesn't take into account loop closures. And there's a specific way to actually deal with loop closures, and that's by using submaps. And what happens when we use submaps is we actually, we say that we are not going to build a global map. We're going to build a set of small submaps that can be defined based on a certain distance that you want the robot to travel before it starts building another submap. And you can have each submap registered to a particular key pose, right? So the good thing there is that you have this entire list of submaps that have their transforms embedded in each key pose. So when there is a loop closure event, the key pose list gets updated, and all the submap transforms automatically get updated with the key poses. So, once you do the final merge of the submap to build this global map, all of that happens automatically with the Keepos updates. So that's something nice that you get if you were to actually use submaps. That's something that we're doing in sub T now, but there's multiple reasons for doing that. We're also trying to share these sorts of maps over the network using John's map sharing ledger, which some of you might have seen in his lab presentation. And a map like this is too big to be transferred monolithically over the ledger. So I basically split this up into smaller submaps, and then each submap gets stored in a particular ledger message and then gets shared. And we have the ability to merge all those submaps to build like large global maps. And then we also have the ability to adjust for loop closure events. So what about the other guys, like all the guys who haven't been able to set things up? Is there something that's I don't quite know if there's anything wrong with the setup, or do you guys need help with anything? But yeah, I mean, feel free to sort of play around with these parameters. Let's try reducing the voxel size and see what happens. There's a max sense distance that I've put as 90 meters here, but you can change that. And what that does is that actually spaces that are if the point is, in this case, if the point is further than 90 meters away, it won't go all the way till the end. It sort of frees it up until 90 meters. So what I mean to say is that if the point in the point cloud is more than 90 meters away from the origin, then what this number allows you to do is that when you're raycasting, it'll free up the voxels until it reaches this max sense distance. So you're freeing up all that space, but it won't mark that particular endpoint as being occupied because the actual occupied point is further away. So it just stops there. But the good thing is that you free up all that space because you know that is free. Okay, let's try running this with the new voxel size. Oh, sorry, I did not launch the node again. Okay, so we have this, and then we have start sort of. So you can see that the voxel size is smaller. You can sort of find more detail. You can go as small as you want. The only thing is it sort of slows down raycasting because it's sort of updating a lot more voxels. But in case you need that sort of resolution, you have the ability to do that. Yeah, so I mean, if you want to use this in your project, I think the first thing that you would probably want to look at is the callback, and sort of, you know, change it according to the kind of data that you're getting. And you can also then modify the update occupancy grid method to sort of suit your own purpose. But like broadly speaking, if you keep it the way it is defined here, then you should be able to achieve similar results. Okay, so I guess I'll move on. Or do you guys need more time, or are you still sort of experimenting with things? Can I get a thumbs up if you want me to proceed? Okay, looks like the majority said yes, so let's proceed. All right. So coming back to the presentation. Okay, so now I'm basically going to focus on frontier-based exploration. There's a lot of ways in which you can do exploration of a priori unknown environments, but I'm going to specifically talk about frontier-based exploration because this is like a huge area and very much active in research. So in case you guys want to sort of know more about this or get into more details, we can do that later on after the talk. And you can always search things yourself as well. Right, so what are frontiers? They basically represent the boundary between known open space and unexplored space. And this is a pretty old concept. I think the most famous paper is by this person called Brian Yamauchi. And I think an interesting fact is that he was actually on the DARPA challenge team with Basti. And Basti says that he's a pretty smart guy. But yeah, it's sort of, you know, these figures are from his paper. And if you look at the figure on the right, basically what's happening is that, you know, you have a 2D occupancy grid. The points that are marked in light gray are essentially unknown points that represent unknown space. And the open space is basically white, right? And then you have the boundary, which are these dark points, dark black points, which are basically occupied cells in the grid. And the ones that are colored in blue are the frontiers, essentially. So so there are different ways in which you can define frontiers, actually. So in my method, I actually assign occupied voxels as being frontiers, but you can also assign free voxels as being frontiers. The difference is that if you assign free voxels as being frontiers, then you are concerned more about free space, right, in any particular environment that your robot is in. But if you define frontiers as being occupied voxels, then you are more concerned with surfaces, right? So the reason why we chose surfaces over free space is because we care more about surfaces, like for the DARPA Sub-T challenge, for instance, because the challenge involves locating artifacts. And that basically means that it has to be somewhere on a surface, right? It's either hanging on a wall, it's on the ground somewhere, it's against a wall. So we only care about surfaces. We actually really don't care about free space at all. So I restrict my frontier search to actually go through only occupied voxels. So, you know, I do some sort of a neighbor, I search for neighbors around each occupied voxel. And based on certain thresholds that I define in terms of the neighbors being known, unknown, free, occupied, I determine whether that particular occupied voxel is a frontier or not. And we'll look into more detail later on over there. But yeah, I mean, I think in 2D, it's pretty straightforward to do. And you can, make that out in the figure here. And one key idea behind exploration planning, which Yamauchi mentioned, was that, you basically gain the most new information about the world by moving to the boundary between open space and unknown space. So it's a very simple idea, and it works decently well, say maybe 60-70% of the time. I think to get full coverage, you need something more. You need to be able to reason a little more about the environment. But we're going to restrict ourselves to just this simpler approach. We're going to do it in 3D and run it in sim, but we'll stick to this simpler idea for the sake of the constraints of this tutorial. This is kind of a small animation that actually shows you how a robot explores the environment in a 2D grid world. So you have these different colored clusters, right? So the frontiers are essentially getting clustered, and their numbers keep changing. I guess that sort of defines, it's a certain ordering of each cluster. And essentially the robot's just planning paths to those clusters. So I think these particular, the crosshair circular points are cluster centroids. And, all that the robot's doing is just explicitly planning a path to each of those. And the map keeps getting updated as it moves through the environment. And we will actually be doing something similar, but in 3D. The idea sort of remains the same. I wanted to sort of also go over a little bit over the autonomy architecture. So there's actually two examples here. The second one is sort of a more recent development. It's slightly more complex, but just to sort of give you an overview as to, how you might want to sort of structure things if you were building your own exploration planner. So on the left, we sort of have the inputs. So we have like a base station GUI, or, in the sub-T challenge, which is kind of where this is from, we have a base station operator who sort of gives commands to the robots and, controls the robot. But in your case, it could be anything. It could also be a piece of code, a script that sort of does that. And we have the perception module, which is basically a Velodyne puck and 3 Intel real senses. They go into the mapping module, and that's primarily Loam that's doing SLAM. We generate occupancy grids out of the outputs from Loam. You can also generate distance transform maps using the occupancy grid, and that can be used. In this case, actually, yeah, John does this separately using directly the LiDAR data. And that is what gets fed into the local planner. So that's the mapping module. And from the mapping module, we actually come to sort of like the behaviors. And starting on the top, you have the global planners. So we had 3 planners for like the sub-T urban competition. We ended up using 2 out of those. The one that I'll be showing is 1 out of those 3. So, basically these planners generate a trajectory, set of waypoints, and those waypoints are then passed to the local planner that generates, local trajectories to get to those waypoints. And you also have other behaviors that the robot can do, and those are all defined as part of a behavior tree. And there's a behavior executive that enables you to sort of switch between, doing exploration using the global planners, or, doing something else like returning to homes, or you want to return to comms, or, the local planner finds that there are new obstacles in the environment suddenly because it's running at a higher frequency. then it wants to rewind, it sort of goes back. And this is quite helpful when, you're flying in sort of like a dusty environment, because it gives the robot time for the dust to settle so that it can move forward later on. Yeah, and then, the rightmost part is the local planner, the trajectory controller, and the low-level control and actuation, which is the low-level decision-making module. And this is kind of, this is what the core central stack does, which was written by John. And there's all these behaviors and the high-level decision-making also, that's part of it. This is a more recent development, and we sort of wanted to modularize our mapping and planning pipeline a lot more. So we, created these different modules. So you have a separate map building module, that produces global maps, produces submaps, produces distance transform grids. And that you can get access to all of those maps using an interface API. And these are, different packages that enable you to access those maps. Then we have something called a map processing module, which actually does processing on the maps in terms of finding useful information in the map. So it'll do frontier detection, it'll sample for viewpoints. We sort of wanted to reason a little more in terms of how we were exploring the environment. So we sort of want to, want the robot to point at a certain orientation when it's looking at a surface. And for that, we do viewpoint sampling. And then, we get these frontier sensor maps, which is to say, basically, we only care about what the cameras are seeing, because the cameras are actually what pick up artifacts, for instance, right? So if you had a search and rescue mission and you're sending a robot into an unexplored environment, you primarily care about the outputs that you see from the camera, right? So you only want to sort of restrict your exploration to that, because the LiDAR, will see so much more. And what that does is, when you're restricting it to only what the cameras have seen, you actually see more, because with the LiDAR, you see so much further out that the cameras cannot see all of that information unless they can get close enough to surfaces. So this is kind of why we use these frontier sensor maps for that. Then we have a separate graph manager that actually builds like a global graph, and that graph sort of, has a history of all the key poses that the robot has seen. And, it can also do things like expand the graph into regions that have been unexplored, so the robot can actually, traverse the graph and get to places that need to be explored, where it thinks there might be more information. And then there is like a separate inter-robot map sharing map module, in which we actually share these sensor maps. And that's done using the ledger. So all these maps are sent over the ledger, and each robot is sharing what it's seen with other robots. And then, we combine all those maps together, and we weigh the frontiers differently based on, whether it's a local map or whether it's a map coming from another robot. And we can sort of, that way we coordinate exploration, as well as we can implicitly define deconfliction between robots. Then we have a planner module that essentially, does goal selection, monitors the progress of the robot along the trajectory, generates paths between where the robot is and where it wants to get to. So yeah, this is kind of like the architecture that we will actually end up using for the next round of sub-T, which happens in October. And this is as modular as we could possibly make it. And this is just to give you an idea as to how, this is one way of doing things. May not necessarily be the best way, but yeah, just an example. Okay, so in terms of the modules, I guess I've spoken about this a little before already, but the exploration tutorial node, it's doing occupancy grid generation, then it detects frontiers within that grid. It clusters them together and then selects, the top 5 clusters to plan to, and then essentially, does RT expansions from the current robot position to those clusters. And then we have a separate module, which is called the drone voxel planner, which was actually written by Fan, who's a student at CMU, who's part of the sub-T team. And that basically does progress monitoring. So it basically monitors the progress of the drone along the generated path, and essentially generates waypoints for the local planner to follow. So now I'll start a walkthrough of the code, and then we can start running things in sim and see how that looks, and you guys can play with that as well. Let's see. Okay, so yeah, so primarily it's the execute method, and it's a bit overwhelming. I did not organize all these crazy functions into I didn't wrap them, but it's not too bad. We can go through it quickly. Essentially, what we try to do is we do a frontier search in a local sort of in a bounding box around the robot. We don't do it globally for the entire map. And yeah, we do that. And this is kind of the method that actually does that for you. Let me take that out. So it's kind of long, but essentially what we're doing is that, we go through this point cloud of points. It's just a template point cloud, which has points that are equally spaced. And this particular point cloud sort of rotates with the robot, but actually doesn't. I used to do that before. But essentially it moves with the robot. So you have a zone around the robot wherein you actually want to search for frontiers. So, you go through each point in the point cloud, you find the corresponding voxel for that point in the grid. And then for that voxel, we actually first check whether it's occupied or not, right? If it's not occupied or if it's unknown, we don't care about it because we're only looking for surfaces. So if it's occupied, then what we do is we basically, do this search for the immediate neighbors. And that's what this does. And we basically, in this case, in this particular configuration, so I've defined the search dimension as being 3, and this actually means the number of voxels. So we will be searching for, we'll be counting the state of the neighboring voxels for an occupied voxel in a cube of size 3 cross 3 cross 3 voxels, right? And that particular voxel, occupied voxel in consideration is going to be centered at the center of that cube. So, so that's what's happening here. And what we're doing is we basically, we probe the value of the neighboring voxel, and we figure out if it's active, and if it's active, what is the value, right? And based on the value, we can figure out whether that voxel is free or occupied, known or unknown, and so on, right? So if the value of the state is false, which means that it's not active, which basically means it's unknown. So then we count that as an unknown. If the log occupancy value, if it actually has a value, which means that it's active. And if it's less than 0, it means it's free, right? So we count it as free. If it's greater than 0, we count it as occupied. So this way we count all the neighbors in terms of their state. And then based on those counts, we can actually we can do custom thresholding to determine whether we want to mark this particular occupied voxel as being a frontier or not. And this is a bit of a hit and trial. I mean, obviously there are standard ways in which you can figure out if there's a if there's an occupied voxel on the boundary, how many known, unknown, free occupied voxels it should be surrounded by. But it kind of gets complicated in 3D, especially if you sort of want to get rid of noisy frontiers, which is kind of what I've had to do. So I sort of, manually tune these parameters. But you can play around with this, and in the config file, if you look at, let's see, hands-on session number 2, then these thresholds are essentially what I'm talking about. So you can actually modify these to generate more frontiers, and you might want that in narrow spaces where you're not being able to generate a lot of frontiers, because this, I mean, I call it a form of noise reduction, although we're not really doing any noise reduction explicitly, in which this form of noise reduction sort of gets rid of too many frontiers. So this is all tunable to allow you to sort of do exploration based on whether you want to just do a coarse exploration in which you're sort of flying around just and not really looking at things closely, or whether you want to do really fine exploration in which you want there to be a lot of frontiers and the robot sort of goes closer to surfaces. So that's something that you can sort of play with to see different behavior in the sim. Yeah, so once we get these frontiers, we put them in a separate grid, which we call a frontier map, and then we do a little bit of clearing out. And what I mean by that is that when we're trying to do like an RT expansion from the robot's current position to a particular cluster centra that it wants to go to, what actually happens is that there's a lot of like unknown space around the robot, because the LiDAR point clouds are actually sparse when it's close to the robot, because you only have 16 vertical lines. So we sort of manually clear out a little bit of space around the robot to help the RRT planner to find trajectories. So that's kind of what is done here in terms of using this particular method. And that's what we're doing here. Essentially, we're creating a little bit of a free space around the robot just to help the planner find paths. And then here we basically, we're sort of marking out frontiers. We're clearing out frontiers and we're marking out corresponding occupancy grid voxels so that they don't get generated again. And that's just to avoid repeatedly exploring places that will keep generating noisy frontiers, and we don't want to get to them because they're kind of inaccessible. So these are just like tiny tweaks that you have to do in terms of trying to get a more robust performance out of the planner. And then essentially, yeah, we basically cluster the frontiers, and the corresponding parameters for that are here. They're called global unvisited. So this is basically a threshold in terms of how many voxels you want to be there in a particular cluster. And you can also define in meters how large you're willing to search around a particular voxel to sort of cluster neighboring voxels into a single cluster. So you can change that. You can have bigger clusters depending on the environment. You can have a bigger search dimension as well. If you have frontiers that are like much further apart and they're sparse, then you might want to increase that dimension. So you can change that, you can play with that. And then, yeah, we sort of, do another sort of marking of these frontiers in the frontier map to sort of, prevent them from getting generated again. And then this is the RT part, but essentially what happens is that, we are looping through the clusters, and the primary method here is basically just this, in which we are basically collision checking for each point. And we use a particular robot model. So right now the robot's modeled as a cube, but that can be changed. It can be a rectangle. It can be a more complex shape, depending on how you want to write your own iterator. But in this case, we sort of put a cube dimension as being 0.6 meters. Yeah, so essentially it's, the RT is sampling for all these different points. And at each point, it tries to search for collisions in a cube of size 0.6 meters, of side length 0.6 meters. So you can increase that, reduce that based on the size of your robot. And yeah, that's about it. So it generates a trajectory, and then, we visualize it, we publish it, and that's kind of how it works. I can now try to run things. I would suggest that maybe you wanna just do a git pull, a git remote update, and a git pull on the exploration tutorial package, just to ensure that you have the latest code, because I was making some last minute changes. But yeah, now we can sort of actually run the sim. Let's see. Here. So we're at this part. And right. Oh, there's one more thing that you need to do, is you need to change the branch for the local planner. So go to the core local planner package, do a git remote update, and check out this particular branch. This was like a last minute change, so I wasn't able to add this to the ROS install. And then in the first terminal window, we will launch Gazebo with the core autonomy stack. And then we open two more windows. In one of them, we'll open the exploration tutorial node. And in the third one, we will run the drone voxel planner, which is basically a progress monitor. Once we run all of these things, then we go to the RQT GUI and we will click on takeoff. You'll have to check if you get any green trajectories, because there's some bug that, sometimes you don't get any green trajectories from the local planner, in which case you might want to restart the sim. And then once the drone has taken off, you can click on explore, and then, it should start exploring. So I'm going to do that now. Let's see. You can minimize the Gazebo window. There's not much to see there. It's basically the world that I've picked is kind of simple. It's like a large room, and it's got like a few walls here and there, but this was actually randomly generated. But yeah, I mean, you can change your world and make it whatever you want later on. But for now, we're just going to use this simple environment. Okay, this harvest isn't working. Might have to restart this. Okay, so this should show up in the RViz. This is actually, this particular point cloud is it, yeah, this is actually Velodyne cloud registered. So this is like an instant, I think it's published at 5 Hertz. So it's sort of like a single scan that you get from Loam. And then what we're going to do is we're going to launch the exploration tutorial and launch the drone voxel planner. So now you should see something like this on your screen. The drone is on the ground. That's the waypoint that it's going to try to follow. So then we click on takeoff and we wait for the drone to complete takeoff. Right. So then you should see something like this. So these green spheres that you see are actually frontier clusters. So I'm not explicitly plotting the frontiers because they can get a little confusing, but just the cluster centers, because this is actually what we're planning to. So right now all the trajectories are red. So there's some bug here which we haven't been able to fix. So I'm just going to restart this whole thing again. Okay. Okay, now we take off. Hopefully we get some green trajectories. Oh no. Okay, gotta keep trying.
Wait, can you just try dragging the drone in gazebo?
Oh.
Maybe like the field of view will change and maybe they'll turn green.
How do I drag it?
Just click on it and then press T on the keyboard.
Okay.
Yeah, now you can move it.
I see, okay. Oh no. Let me check RViz. Okay, we got some green trajectories, so that's good. I'm gonna click on explore now. Oh no, they went red again. Okay, let's try moving it a little bit. I guess I should restart this.
Hey, Rohit.
Hey.
So I've tried running this a few times, and I can't get the frontier clusters to show up.
Really?
Mm-hmm. Now, when I'm running the, I don't know if this matters, but when I'm running the voxel planner, it's complaining about in initial trajectory message is currently empty. Is that normal?
Yes. That's okay. Actually, what happens is that you're not, maybe it's in the initial stage because of which, like, it's not gotten any maps. So what happens is initially at startup, we just send it like a dummy waypoint just ahead of the robot just to get it to move. And then it starts getting maps. And then once it starts getting maps, it actually starts generating the frontiers.
Okay, so is there something I should restart to?
Are you getting a waypoint?
Yeah, I mean the drone's moving just fine. It's just the frontiers aren't showing up.
Aren't showing up. Are you getting trajectories, like these red trajectories?
Yeah, I mean, like I see everything the same thing you do. The only difference is I don't have the little.
Okay, so it might just be like an RViz thing. Can you look at maybe opening like a point cloud message and going to checking this particular message out, unvisited global frontiers. Also, it might be possible that maybe you're running like an older commit, because that was like one of the last changes I did. So maybe you want to do a git pull and catkin build and see if
I did pull exploration tutorial again, and then there's no updates there.
Okay. Did you do okay? No updates. Okay. Yeah. Can you try plotting this to find those?
Try pulling the what?
This particular message, unvisited global frontiers in your RViz. So it's basically a point cloud message.
Yeah, I mean nothing's showing up for that topic.
Okay. So a ROS topic echo doesn't show up anything?
Yeah, when I do ROS topic hurts, there's no new messages.
Interesting. Can you try restarting everything? That doesn't make sense.
I've restarted it like 3 times so far.
Oh. Let me try to get this to run on my system. Then try to debug the issue. Do you also get this message from the exploration tutorial note that the global map is empty? Okay, so now we have exploration. So there are these red trajectories that pop up from time to time, and that's kind of like the RVD expansion that happens, which is basically a set of waypoints that are trying to take the robot to like the next cluster. And the drone voxel planner essentially sort of latches on to these trajectories and ensures that the robot completes a certain percentage of each trajectory before switching to a new one. So you can see like these clusters, they start getting cleared up. And right now, the way I set the frontier params, there's not a lot of them getting generated, and that's for multiple reasons that I'll sort of show you in the config file. but yeah, this is sort of like a more coarse exploration that, you also might sort of not explore the entire environment completely. Andrew, are you still having the issue?
I'm just cleaning my environment and rebuilding, just to see maybe,
Okay. Can
maybe
you
something got
check,
messed up.
what was I going to say? Can you check what branch you're on in Core Gazebo Sim? And make sure that it's rgarg/tutorial.
Yeah, that's correct.
Okay. Just do a git remote update to make sure that it's the latest one.
Okay, they're showing up for me now.
Okay.
It's just probably something got messed up in my.
Yeah, I think like sometimes like cat can build caches things and it won't like update them. So it was probably something like that. So, if you want to look at the config, let's see. What's interesting here is, let's start with these parameters. So these are sort of like, that's a pretty big box actually around the robot that we're saying that, this particular region around the robot is seen and visited. So don't update this region anymore, clear out all the frontiers, and, let's not worry about this region in the global map anymore. So if you want to maybe, comment this out, and this is kind of why, the exploration's kind of a little coarse. If you want to comment this out and maybe go for a smaller number here in the second config and restart, then you'll see a slightly different behavior. this.
Okay, I have a general question.
Mm-hmm.
So for when you guys are, tuning your parameters and deciding this for something like sub-T, how do you balance the trade-offs between, wanting to, cover as much of the region with the camera as possible versus like wanting to be able to explore as much, unseen area as possible within like the flight time of the drone? Right?
That's all, yeah. I mean, that's all down to testing. That's kind of why we do so much testing, because it's very hard to sort of replicate the environment in sim. And you sort of need to go out there to the test site and sort of run different configs to sort of figure out what's the best compromise. Yeah. So we actually, you've been to Hawkins, right? Have you been to that large pillar room?
Yeah.
Right. So there's like there's a corridor that sort of leads out from it, right?
Yeah.
And we had a lot of trouble getting the drone to go to that corridor because that corridor would sort of, it would come up in the sensor's field of view in passing and wouldn't generate a lot of frontiers. So, I had to sort of tune the parameters a little bit to generate more frontiers. But that, sort of has an effect on the rest of the environment in which, you're getting too many frontiers. But initially, when I wasn't generating a lot of frontiers, it would just stay stuck within the pillar room because it just cannot get enough frontiers to sort of pass through the doorway. But then, I tuned that and I started getting more frontiers. So then the drone actually, explored the entire pillar room and then went into the corridor, which was nice. So there's a lot of such situations which come up, and we sort of just have to, tune all these different parameters to get it to work.
And another question is like, how do you, I don't know if you mentioned this, but how do you handle like, if you're constantly jumping between two frontiers, do you like maintain and you say like within 5 seconds, I'm not going to change frontiers?
Yeah. So there's a lot of ways in which you can do that. Like you can lock on to a particular trajectory, right? And you can say that I'm going to complete at least 70% of the trajectory before I shift to another trajectory, right? And that can be also defined by how much further out you actually want to see, right? So if you're only considering what the LiDAR sees, then you can actually see so much further out. And you may not necessarily need to complete a large part of the locked trajectory because the map just gets updated so quickly, right? Because it sees so much further out. So you can have a low percentage of that trajectory completion threshold and switch to something new.
Cool, thank you.
Yeah, so actually we have the drone voxel planner sort of does that. I haven't gone through the drone voxel planner because it's a bit of a mess, and I never really got the time to clean it up before the tutorial. So it would be better if you guys just treated it like a black box because it's a big mess. But essentially know that it does progress monitoring and handles all these different trajectories that the exploration tutorial node keeps generating.
Hey, Rohit.
Hey.
When we run the simulation, are we supposed to see the frontiers and the maps?
Yes. So you should see something like this. Do you see something like that?
Oh, yes, yes. And right now the simulation is running. The drone is exploring the room.
Okay.
But I can only see the odometry, but no maps or frontiers
Oh, really?
in our base.
Don't you see these blue colored points?
No.
Okay, so let me try to run this here and show you what I'm talking about. So do you see these green spheres in your setup?
No, I don't have this green points.
Okay, so maybe you want to like do a cat can clean and rebuild the workspace and check if you have the latest commit on both the exploration tutorial and core gazebo sim.
Okay, I'll do that.
Yeah, and if you have trouble, so I actually sort of, you can see the grid here, like these very faint blue voxels. I actually made them faint just to make them, you know, easier to like blend in, but you can increase the size. If you go to the global awk map and click on size and make it like 5, then you'll be able to see the grid more clearly like this.
Yeah, okay, I'll try to rebuild the workspace first.
Yeah, yeah. Yeah, so I think like so what I did with the config was that I, you know, reduced the dimensions of that clearing bounding box and made it much smaller. And, you know, the effect of that is that it's sort of like, you know, going closer to surfaces, and you will also, as a result, see slightly oscillatory behavior, like in this case. So there's no optimization that's happening, right, in terms of actually planning a set of waypoints. You know, we're only sort of greedily picking whatever the next best cluster is to go to, and you know, going there. So that can sort of lead to oscillatory behavior, and also, you know, the path doesn't really look that optimal. So I haven't done that here, but like one way to do that, one way to deal with that issue would be to, you know, do some sort of an optimization in terms of saying that, okay, you know, globally I have these regions that I want to explore, and you know, you could try to solve some sort of like a traveling salesman problem, right? Formulate it as a TSP and say, you know, this is kind of like the most optimal path that we can take with the drone in order to effectively explore all these different regions. In this case, that's not happening. It's, you know, purely doing like a greedy exploration. Yeah, so, you know, some sort of an optimization can be added to this to sort of get more optimal coverage as well as exploration. And, you know, if I were to sort of change the cluster thresholds, right, make it bigger, say make it 50, and, you know, keep the cube dimensions the same, then, you know, you'll see fewer clusters here. And, you know, they might be more spread out. Then we can also sort of mess with these thresholds to sort of generate more frontiers in case, you know, we're in an environment where we can't get a lot of frontiers. Typically what that would mean is that you, let's see, you reduce the minimum unknown box count threshold, and you increase the max free box count threshold. And you can also expand these two limits. So make this like 0 and make this really high, so that, you know, you're expanding the ranges essentially. And that'll like generate so many more frontiers. So yeah, I mean, you know, this is a greedy approach. So there's also no guarantees for, you know, coverage, right? And you will see that there are areas that the robot misses out, because we've sort of, you know, either cleared them out and there's no frontiers being generated there, or it just sort of, you know, misses them. In this case, it seems to be doing okay. So this behavior, you know, for a greedy approach doesn't look too bad. You know, broadly it sort of follows the walls, and you know, that's kind of what you want it to do. Then it sort of, you know, goes, explores the roof. There's not a lot of frontiers being generated on the ground because they're sort of getting cleared out. But we can sort of change parameters and sort of, you know, have more frontiers being generated on the ground. So now I think it just sort of, it'll just move around randomly, because I haven't really added any sort of an end condition. So it's just going to move around randomly. So we can play a little more with the parameters and see what can be done there. Let's see. Yeah. So what if we reduce this to say 10? Increase this to 8. So let me try to restart this. Let's try to restart our viz. Start. Okay. That. So we have that. I'll take off. So now you can see that we're also getting frontiers on the ground. So, we can, hopefully it should explore that stuff as well. Are you guys able to run this on your system? Any problems, any issues?
Yeah, I'm having a question. So for me, the GUI just doesn't pop up to like say take off or anything. Like everything that comes up like Gazebo and Arviz, just not.
You're not getting this?
No, yeah, that doesn't show up for me.
Can you look at, let me see. Is John there? No. John, do you know which node launches that GUI?
It's RQT. It's capital A on Monarch.
Oh, right. Capital A. Can you check if RQT has crashed on Rosmon? This particular one? And maybe you can restart it and see if that shows up.
Well, because I've run it a bunch of times, and I've just never had luck. They've probably tried it 6 times, something like that.
So it's never launched?
Yeah, it's never launched.
Oh.
Maybe I'm missing some package or something. Go back through and see.
Was it launching when you ran John's Core Central stuff yesterday?
Let me see if I can remember if it did. I think it did. I might not have noticed though because Gazebo comes up and everything else came up. I might not have noticed if it didn't even come up. Let me go back. Oh, I think I found it. Looks like it's a IQT. I'm just gonna go install that.
Oh, okay.
Yeah, it looks like it is.
Hey, Rohit.
Hey.
I think I get everything running this time.
Okay, cool.
I was making a mistake in my RV settings. I'm using the world frame, so
Oh,
nothing
okay.
show up because the TF is wrong.
Oh,
I change it to map,
map.
and then everything pops up.
Okay. Okay. Cool. Cool. Yeah. So what I did now was I actually reduced the number of voxels, like the threshold number for selecting clusters. So now we should get more clusters to explore. gonna have to time these red trajectories.
Hey, Rohit,
Yeah.
what happens if there's not any more frontiers?
Yeah, so that particular end condition is not defined in the behavior tree. I mean, there's like additional signaling that actually happens. So like for our sub T, I haven't defined that in the tutorial, so it just sort of keeps flying around randomly. But like for a sub T robot, we had I think two behaviors. One was it would either return home, or it would try to return to comms. And it also sort of considered the battery life. So if, you know, while exploring, if it's not completely explored an environment and it sort of runs out of battery, then it'll try to either do like a landing at that very spot or try to go back. So so those are behaviors that are not designed in this tutorial, but we had like some form of a signaling mechanism in the planner that would tell the behavior executive that, yeah, it's, you know, we're not finding any more frontiers. We actually had a backup planner in addition to this planner, which is sort of like a graph-based planner. And what that would try to do is that it would build this key pose graph, which was basically a history of all the key poses that the drone has been to. And it would try to use that graph to sort of try to take the robot to a location that it hadn't been to before, and sort of try to see if the planner sort of, you know, finds more frontiers there. And even that had some sort of a signaling mechanism in which if even that failed, then it would sort of signal the behavior executive to be like, yeah, let's just go home or let's land.
Okay, thanks.
Yeah, so there's a lot of like, you know, damn it, I missed that window again. It's all red. But yeah, I mean, with regards to building like a complete autonomous solution, right, in which, you know, it takes off, does the exploration, you know, ideally you want it to keep exploring until it runs out of battery life, and then, you know, it either tries to come back to communications or it lands depending on the state of the battery. These are all like additional behaviors that, you know, you need to think about in addition to, you know, just sort of trying to explore the environment. I mean, I guess John has probably spoken about this. So we use like a behavior tree for that, right? And we can add more behaviors to the behavior tree and sort of switch between them. Either we can do it autonomously, which then requires some sort of a signaling mechanism between all the different nodes that are involved. Or we can also have like the base station operators sort of engage some of those nodes. Yeah, I think there's like I think at the end it sort of just all goes red. So you want to maybe click on explore right before it goes red, and then it should be fine. We never really had this issue with the other sim, but yeah, this John didn't really get much time to sort of look into this. So kind of why it's like this, but yeah, eventually, like we'll try to have this fixed and pushed so that you know, in case you guys want to run more tests, you don't have to face this issue again. Damn it, missed it again. Okay, I'll try to move it like John said. Let's see what happens. Okay, well, that worked. So if you click on the drone and you get this box, and then, you know, if you just move it along, say the green axis, then it should find trajectories and it should start moving. So that's like a quick fix for this issue. So yeah, feel free to like, you know, experiment with these config values. You can also, you know, some of the clearing out that I'm doing, you can even sort of get rid of it and see, you know, how the drone behaves in that case when, you know, when you have too many frontiers to deal with, or, you know, things like that. So I think there's primarily you just want to sort of look at the execute method and you know, go through what's going on. It's sort of like in a stepwise fashion. And I think the code is fairly readable for you to be able to make out what's happening. And yeah, if you have any doubts or any further questions, you can let me know now or even later on when you're working with the code. But yeah, I mean, that's kind of all I have for the tutorial today. Yeah, that's it. So yeah, let me know if you guys have any questions or if you're having any issues, and I can sort of help you out with that. We also have these random world generators that I might be able to port over from our sub-T project. So this particular environment was generated using that. It was actually written by a master's student at Oregon State, and it's pretty cool. Like you can you can generate a building with like multiple levels, and it can have holes between the floors. You can sort of randomly define walls. You can you can have them as long or as short as you want them to be. We also have like a corresponding random cave worlds generator, which does something similar, but they're like cave-like environments. And even otherwise, I think you might also be able to find some worlds in the DARPA sub-T repo online if you search for it. Although they've sort of shifted away from Gazebo and they're using Ignition, which is a slightly different version, but I think they have some old worlds that you could also sort of just plug in and play with. So I guess I'll end in a few minutes. Let me know if anyone has any questions or queries or any issues with running this stuff. And then I guess I can close out in a few minutes. If you want to know more about OpenVDB and how to work with it, you can just go online and search for this. Their documentation is pretty good. They also have like a cookbook, which, you know, bunch of self-explanatory code. They also have an overview, which is kind of nice, that tells you, you know, a high level what really goes on with the grids. The author actually won an Oscar for this. It's actually an Oscar-winning library. So the main author, Ken Museth, was actually he was given an Oscar by Margot Robbie. I don't know, a couple of years ago, which was pretty cool. And I think you can find his, this is the publication that, you know, you can sort of go through. It's on his website, in case you're interested in this particular library. Yeah, it's a bunch of things. Yeah, now it's done. So it's not complete coverage, but, you know, you can hand tune the parameters and try to get it to cover as much as possible. So yeah, I think I'm done here. Thank you for attending this tutorial. I'm available on Slack and on email in case you want to ask me any further questions, but I think I'm done for now. So yeah.